Now we are discussing GATE 2023 question number 19. John and Jane independently performed thermodynamic experiment in which X and Y represent the initial and final thermodynamic states of the system. So let's say this is my state 1 and this is the state X and state 2, which is the state Y according to this problem. And John performed the experiment under reversible condition. So let's say he has done this experiment. How this can be done under reversible condition, we'll discuss that later on. In fact, reversible condition is an ideality, but we can approach reversible condition. So this is done by John. So this is by John, and for which the change in entropy is delta is reversible. So this is my delta is reversible. Jane performed the experiment under irreversible conditions. So she has done this experiment under irreversible condition. Normally, whatever the experiments we do, everything is irreversible. The extent really differs. So this was done by Jane, and the change in entropy is delta is irreversible. So we have to find out the relationship between this delta is reversible and delta is irreversible. Very simply, we know that entropy is a state function, just like internal energy, enthalpy gives energy, etc. And its values depends only upon the initial and the final condition, not on the path followed. So whether you have followed by this method or this method, whatever, the change in entropy is calculated by the value, the difference in entropy between this state 1 and state 2, or between X and Y. Does not matter which path you have followed. So therefore, delta S reversible must be equal to delta S irreversible. So A is the correct option. Now, let us try to understand this is little deeper. We'll try to see a chemical engineering application. Let us say we are cooling a light hydrocarbon vapor stream under reversible process. As I said, reversible under reversible process is as an ideality, but we can approach this one by doing it in an extremely small steps or infinitesimally small steps. Let's say this is my hydrocarbon vapor, which is at 500 Kelvin, and we are cooling it to 300 Kelvin. This is my initial state S1, and this is my initial state S2. So large number, infinite number of small heat exchangers, where delta T would be infinitesimally small in each heat exchanger. If this can be done, then we can say the change in entropy between these two states is going to be equal to reversible. It's a reversible process. And of course, we're assuming constant pressure. So change in entropy is given by this expression here. So this is natural log of T2. So I'm assuming certain value of Cp. And you can see this is 15.324 negative because heat has been taken out from the system. So this is the change in entropy by the reversible process. Now, if we do it by the irreversible process, which could, before that, let's just look into it. What was the change in surrounding their entropy? Of course, because this is going to be the same because it's a reversible process. So therefore, as you can see, for the surrounding, this is the definition of entropy. And since delta Q system is the same as delta Q surrounding, the amount of heat that has been taken out has been put into my surrounding. That means the what is the water temperature or the coolant temperature. So this would be a positive value. There's negative, right? So this would be a positive value. So the entropy generated would be equal to zero, since this is a reversible process, and total change of the universe entropy would be equal to zero. Now let us see if we do the same thing by the irreversible process. Standard, let's say, a heat exchanger. We're going 500K to 300K, and only thing we are assuming that this is sufficiently large amount of water or the coolant is flowing, so that the change in temperature is not essentially there's essentially what the temperature is coming in, temperature going up, which again is impractical. But let us assume that. So the change in entropy is 15.32, which we have got here, will be the same, because this is done by this equation here, done by this equation here. Okay, and this equation, whether you do it in extremely small steps or one step, so this equation, that is Cp ln of T2 over T1, remains the same. So this value, whether you do it by the reversible process or the irreversible process, remains the same. And the change in surrounding value, of course, as you can see, is delta Q over T. I'm assuming a certain value of Cp, and you can see, and it is doing at a constant coolant temperature, so plus 20. So there will be some amount of entropy generated, which is, of course, the state of the system, and this is the surrounding. So that's the amount of generated. So this is the entropy generated due to the irreversibility of the process. But the change in entropy of the system of this fluid here, of course, remains the same always, whether you do it by the reversible process or the irreversible process. Let us try to see an example, another example, practical example of the industry. Let us say we have a steam line, and steam is available at 10 bar and 300 degrees Celsius, and we have to get the steam at 1 bar. There's a normal atmospheric pressure and 300 degrees Celsius. Okay, so this can be done in two different ways. One way is just put a put a throttling valve here, and assume this to be adiabatic, no heat loss, well insulated. And this is actually, so that's the one Jane experiment, irreversibility. And of course, since this is throttling under a adiabatic condition, this is an isenthalpic expansion, we know. And of course, therefore, the temperature here and that is 300 degrees Celsius will be the same as temperature here, 300 degrees Celsius. But that is only on the assumption of ideal gas. If this throttling is done for a real gas, we know there'll be a drop in temperature, which is the Joule-Thomson effect. That's a separate discussion altogether. But we, so this is my irreversible process. This is a sudden expansion, irreversible process. What could be a approximate reversible process? If we just let it expand very smoothly, let's say to a turbo expander, again, that is that adiabatic. And if we do that expansion, of course, there'll be a drop in temperature. So the temperature, it has to be heated up. It has to be heated up. And so this is an isentropic expansion. We know that. Okay. So there's a smooth expansion. That's an isentropic expansion. This is isenthalpic and this is isentropic. And so this has to be, whatever the temperature drop from here, it has to be heated up. So this is a heater, heated up to increase this temperature to this part right here. So we can get this steam here from this steam. This is the initial state. This is my final state, either by this irreversible process or by this reversible process. Here, this is my reversible process, but this, of course, is going to be irreversible. Okay. Anyway, so let us see how we do the calculation. As we said, whether we do it for the reversible process, that is by the John or John or Jane, either way, the change in entropy, we know this is the expression here. Since T2 is a T1, that means the initial temperature here, T300, is the same as a final temperature. Does not matter how we have gone through this, whether by this process or this process. We'll just look into the final state and the initial state, and this is 300 degrees Celsius, 300 degrees Celsius, temperature remaining the same, only the pressure has changed. So the calculation of change in entropy would be this one. So this T2 is the T1, so this is equal to 0, and this negative of this one, I'm assuming certain values, we do that, and that's 19.14 kilojoule per kilomole Kelvin. This is 1 bar and this is 10 bar. And for the irreversible process, that is by Jane, we know this is the equation for the flow system. So this is the change in entropy between the initial and the final state. Since this is an adiabatic process, so this Q dot is equal to 0. So this term is equal to 0. So S dot Gen is the change in entropy of the system. Okay, that is by the irreversible process. Okay, this one right here. If we do the calculation for the turbo expander. So this is my turbo expander, as I say, isentropic process. So the entropy here and the entropy here remains entropy here, and the entropy here remains the same. So the change in entropy across this one is equal to 0. And we know this is the equation for that. I'm assuming a certain value of gamma. Actually, this is probably around 1.2 to 1.3. But anyway, so if we do the calculation, we see this is a 297 K. So because of this isentropic expansion, the temperature here would be 297 Kelvin. Okay, now it has to be heated up. So during heating up, of course, there will be a change in entropy of the system, which is now, of course, this one, long T2 over T1, because the pressure remaining the same. Okay, if yeah, so this has changed to 1 bar. So this is at 1 bar, this is at 1 bar. So pressure remaining the same. I'm heating it from 297 to 300 degrees Celsius. 297 K. That's around 24 degree, approximately 24 degrees Celsius to 300 degrees Celsius. So if we do the calculation, so again it comes 19.71. So the actual change in entropy really happens right here, because change in entropy is equal to 0. Because as you can see, the change in entropy of the system, that is of the steam, was 19.14, which we have calculated by this method. And how this has happened? This has actually happened here. The change in entropy is 0, but the change in entropy really happened right here. So this is just an example of how we do the entropy calculation for actual process systems in a chemical industry. But finally, just coming to the solution of this problem, as I said, whether you do it by the reversible process or the irreversible process, as long as the initial and the final states remain the same, delta S reversible should be equal to delta S irreversible. So this is A is the correct option.